Welcome to my IPv6 Fundamentals Chapter 7 SLAAC review. Again, all of these PowerPoints were created by Rick Graziani. All of the credit for all of this work goes to Rick Graziani. So first of all, what's SLAAC? SLAAC is Stateless Address Autoconfiguration, SLAAC. We are doing Chapter 7 into the IPv6 Fundamentals book written by Rick Graziani. These PowerPoints were created also by Rick Graziani, and additional videos can be found by him as well. So let's get into what is SLAAC. And we're also going to be talking about ICMP version 6 in D. So again, we're dealing with SLAAC, but we're going to be talking about a few specific things like DHCP and DHCP with SLAAC. We're going to talk about that in Chapter 8, which is the chapter after this. We're dealing with global unicast addresses in a dynamic state. We're dealing with the first option, again, just SLAAC. So, in IPv4, dynamically assigned addresses we got from DHCP. Basically, a client would come in and would do a request, which should be a broadcast to a server. The server would then go, here is your address, subnet, default gateway, and DNS. That's how we would be able to get the appropriately dynamically assigned IP information. ICMP version 6, Internet Control Message Protocol, as described by RFC 443, deals with the IPv6 version of ICMP. It's much more robust than ICMP version 4. It has a lot more new features, better improvements. It's more than just messaging, but how IPv6 conducts its basic business, including things like neighbor discovery, also known as ND. RFC 4861 deals with the neighbor discovery portion of dynamic addressing. ICMP version 6 we talk about further in Chapter 9, and ICMP version 6 neighbor discovery more in Lesson 10. You have to keep in mind, this is such a huge portion of IPv6. They have dedicated chapters just for ICMP. So again, SLAAC is one, SLAAC ICMP is a second chapter, ICMP by itself is a chapter, ICMP neighbor discovery is also a chapter. So just this portion of dynamic addressing is huge. ICMP version 6 by its neighbor discovery is again 4861. It deals specifically with router solicitation and router advertisement messages. And this is important when it comes to dynamic address allocation and association. So again, a device should come online and it should be able to send a router message. That'll be a router solicitation. And then the router should respond with an advertisement. So the neighbor solicitation, same thing, except it's going to a neighbor. This was predominantly how an IPv4 ARP with DAD would work. So it would redirect messages similar to ICMP version 4. So again, the router advertisement will actually send advertisements to PCs. It's sent periodically by an IPv6 router. When the router receives a solicitation message from a host, it should also resend it as well. It'll be done via multicast, and once the router gets a router solicitation, it will automatically trigger a router advertisement. Again, all of this will have the appropriate IPv6 addresses assigned to it, whether it's a global unicast address or a link local address or a combination there of both. So with all of this, we may no longer need DHCP servers because there is a DHCP version 6 server, but they may be going away. So again, the router advertisement message is part of the ICMP version 6 protocol. The router advertisement messages are sent by specifically an IPv6 enabled router. And you do that by, again, just by turning IPv6 on. So the second you issue the IPv6 unicast routing command, it automatically sets the IPv6, the router to be IPv6 and to start sending periodic IPv6 router advertisements. It will forward packets. It will enable IPv6 static and dynamic routing. It will also automatically enable sending of ICMP version 6 router advertisements. Routers can configure with IPv6 addresses without it being an IPv6 router. It just won't do things like route or forward IPv6 information. So, how do we do all of this? The first command you have to do is tell it IPv6 unicast routing. That turns on the routing functionality for IPv6. So, we have a few different ways to do this. Option 1, SLAAC with no DHCP. Basically, the router will act as everything that you need. Option 2 will be SLAAC with Stateless DHCP version 6 for this DNS functionality. Here's my information, but you need to get other information such as DNS from the DHCP server. So the stateless portion of the DHCP will not hand out IP information or subnet or gateway information. It will only hand out DNS information. Or you can say do everything via DHCP. So even though the router will be an IPv6 router, and it may even send a router advertisement, it may actually say send everything to that DHCP server. So this is going to be dependent on your environment and your circumstances. Option 3, you may need to control the SLAAC process with router advertisements, basically the prefixes, how they should be used. Otherwise, in systems will end up with the DHCP and SLAAC address, so they may end up with both. Again, option 3, stateful, addresses received from the DHCP server. Option 1, stateless configuration, the router hands out all addresses. Options for both. So, if we were looking at options 1, 2, and 3, all options will send out a router advertisement. But it depends on what flags are in that router advertisement. So there is an other configuration flag and a managed configuration flag. So things like IPv6 with a global unicast address with no auto configuration command, basically the other configuration flag set will be able to succeed in getting Windows 7 to populate one address. Both flags are set to 0 in option 1. Using the router advertisement, all addressing information will be sent from the router. No additional information via IPv6. So the first portion, the other configuration, will be set to no, 0. When you want to use option 2, you want to have router advertisements hand out the IP addresses, but you want additional information configured via the DHCP server. Other configuration will be set to 1. Manage configuration will be set to 0. Manage is the portion that will actually handle the addressing of IPv6 addresses. Again, if you're using option 3, you're going to be setting the manage configuration to 1. That will actually tell it to use DHCP instead of the router advertisement addressing. The client will need to get all information from the managed information from a stateful DHCP version 6 server, except for the default gateway, because the default gateway can still have the link local address of FE80 and whatever the link local address is for that IPv6 router. The other two flags include autonomous address configuration and on-link flags. Those are all discussed later in Lesson 8, and the on-link flag is part of the scope of this book, so you can actually learn about that via his videos. So the router advertisement messages, again, options 1, 2, and 3. If we're dealing with option 1, flag will be 0, 0. We're dealing with option 2, other configuration will be checked, managed configuration will not be checked. That way IP will be managed from the router, and additional information will be managed from the other configuration. If we're choosing option 3, it will be other configuration set to 0, and managed configuration set to 1. Because other configuration would just kind of tell it to access the DHCP server anyway. So if we're managing everything from the DHCP server, having both set to 1 would be redundant. Again, we're discussing almost all of them more in depth in Chapter 8. So, again, just by issuing the IPv6 Unicast routing address, it turns on SLAAC, option 1. Allows the device to create its own IPv6 global unicast address without the need again of DHCP server. The prefix will be issued from the router advertisement. That way the devices or the client will know both the prefix from the router advertisement, and it just needs to come up with my own interface ID for the appropriate global unicast address. Again, we discussed the interface and we discussed the global unicast addresses in previous chapters, so that should make sense. Again, we're going to be doing that interface ID with the EUI64 and that random 64-bit value. That, again, completely removes the need for DHCP version 6. But again, how do we get information such as DNS? That's where we really want our DHCP server, because we can ignore router advertisement messages and we can get everything from that DHCP server. Even though that's a farce, sorry, RA will still issue things like its default gateway. Even if most of the IP information, the IP subnet DNS, will be issued from DHCP, the router advertisement can still issue things like it's a gateway. So you can ignore portions of it. But the hosts cannot ignore the default gateway portion of the router advertisement unless it's manually configured. So let's get on to the interface EUI64 portion or the random random value portion. Again, we can have this obtained automatically, whether it be Mac, Windows, or Linux. Again, router advertisement. We may say use an FF02 all devices. That'll be coming from the message. It will be coming from, FF02 is a unicast address to all IPv6 addresses coming from its link local address. Here's the prefix to where first 3 hextets are locked in, even though the :1 is actually the beginning of the 4th hextet, so we have the remaining 64 bits to play with. So the prefix length will be 64. The remaining 64 bits, or 4 hextets, are there. So things like the domain name and DNS server lists may be included if the router and in-system support the appropriate IPv6 RA options for DNS configuration, also known as RFC 6106. What ends up happening is it'll take the prefix, lock in the first 64 bits, and it will use the gateway, the link local address of the router, and it will add the plus interface ID. And that will be based off the MAC address, because it will go through that EUI 64-bit process, which we've already discussed. This entire purpose removes DHCP. So how do we get that 64-bit interface ID again? That will be done through SLAAC. The EU64-bit process, the EU64, not 64-bit, but EU64 process is known. Or we can have a randomly generated address. That will be done also through SLAAC. That will be a privacy extension. EU64 is available for Windows XP Server 2003. Newer is going to be more of the random 64-bit addressing. Mac operating system still use EUI64. Linux is that random portion. So let's talk about the EUI process first. Here we have our MAC address. We're going to use the first 24 bits, which is the OUI, and we have the remaining 24 bits, which is the device identifier. The organizational identifier will be separated, and they will add FFFE in between the organization and the device identifiers, which we've discussed before, but we're also going to flip the 7th bit on the far left. That's going to be the UL bit flipped. So that then generates the new address. If you want to see this, we can actually do an ipconfig. Again, you're going to be looking at the second 64-bit group, because again, the network portion is going to be the first 64-bit. You should be able to identify the FFFE portion. Again, that 7th bit should be the second hexadecimal number. Break that into binary, you should be able to recognize that. Again, you're going to notice that our link local address is going to be similar to our global unicast address portion. Our default gateway will be our link local address for IPv6. So a 64-bit interface ID and the appropriate EUI 64-bit process accommodates the specification for a 64-bit MAC address, because there's a 64-bit boundary process. So, how do we get this random process to work? That's that randomly generated number. So again, we will ignore the SLAAC address, and the second group is the second group of 64 bits will actually generate its own unique 64-bit number. It has nothing to do with the MAC address. Notice no FFFE. So again, if we do the appropriate information, you can also do things like neighbor discovery, RA, DNS, and then list the DNS server. So this will configure a DNS server with the appropriate IP information, and it'll be advertised in a RA advertisement. RA advertisement or a router advertisement. So we can actually go to the interface on the LAN, tell it IPv6, neighbor discovery, RA, DNS, server, and then do the appropriate IPv6 address, and then we give it the lifetime. That will include the information of this DNS server in the router advertisements. You can also then set the appropriate IPv6 global address or link local address on that same interface. And then the router advertisement will advertise all of it. SLAAC is stateless. no entry in the DHCP server. It maintains a state address to device mapping table. It should have both a global and link local IPv6 address. So how can we guarantee the address is unique? So before we use DAD, duplicate address detection, the neighbor solicitation, neighbor advertisement, basically it will send a solicitation if nothing is received, then it is a unique address. If something is received, it's a duplicate address. So once required for all Unicast addresses, RFC was updated that data is recommended. It is only recommended, not required. 64-bit interface IDs, gotta get rid of that. So moving on to the next section, this will be configuring a router as a SLAAC client. So a router not enabled as IPv6, what if we wanted to get IPv6 addresses? So member of all IPv6 routers have a specific multicast group, that's that FF02::1. It will also be given a link local address, that will be the FE80 address, and it will also be given a global unicast address. A lot of IPv6 addresses being issued to devices. All IPv6 routers, same as a non-IPv6 router, should get everything, but members of the all IPv6 routers will get a specific multicast address, which will be a unicast FF02::2 address, and that will be for the appropriate all IPv6 routers, not just the all IPv6 devices. Because again, FF02::1 is devices. FF02::2 is all IPv6 routers. This will send the appropriate ICMP version 6 router advertisements to its appropriate interfaces. And this should be allowed to enable IPv6 routing protocols, things like next generation RIP, OSPF version 3, or EIGRP IPv6, which we are going to be talking about this in. If you've done any CCNA type courses, you should be covering this in your routing and switching essentials type course, setting up both OSPF and EIGRP and RIP, basically. Well, at least a little RIP. I know in my routing and switching essentials course, I did both OSPF and EIGRP. I don't remember if I did much with RIP. You can also do things like forwarding of IPv6 packets. That way, the router will translate them. If you want to program an interface, you would go to the appropriate interface. Here we have an IPv6 router. We'll send a router advertisement to a client. Here, we're assigning both a global unicast address and a link local address, and returning an IPv6 unicast routing. On the client side, all we need to do is turn on IPv6. It will create its own link local address. You can also do the IPv6 address autoconfig default, and then no shutdown and turn it on. It will then accept router advertisements, and it will get the appropriate global unicast address automatically, and that will be sent from the appropriate IPv6 router. So how can we verify the router advertisement messages? You can do a show IPv6 in the appropriate interface, and it will tell you the protocols and the appropriate link local addresses. It should also issue its global unicast address and its appropriate subnets and the group addresses that it has joined. It should also tell you the neighbor discovery router advertisements and when they're sent. Hosts are stateless auto-configuration for addressing. So if we want to verify the client, it'd be show IPv6 interface brief. Similar to show IP interface brief, but this will show just IPv6 portions of the interface. It should show the appropriate interfaces, their status, and their IP information, both a link local and global unicast address. You'll notice here we have an FF/FE address, so this is using SLAAC. Again, if you double check the appropriate MAC address, you can verify that it is using SLAAC and not the random generated 64-bit. Because again, we're using the EUI64, not the random portion. If we want to just look at the the IPv6 routers and their specific routes, you'd be doing show IPv. Oh, I clicked too many over. If we want to do IPv6 and we want to look at its routes, you'd be able to do the neighbors discovery and all the appropriate routes that it has in its routing table. Again, you should be able to see the neighbor discovery and the appropriate addresses and how they're learned. If it's learned via ND, that's neighbor discovery. The prefixes learned via its neighbor discovery should also be there. Again, it should be NDP, neighbor discovery protocol. All right, let's move on to the enabled clients and our specific network. So we're probably already running IPv6, which most organizations are, most PCs are, most networks are. If you have anything above Windows Vista or a newer version of Mac OS X or Linux, you're already having IPv6 functionality. Now, do you leave it turned on? That's a whole different story, but it's there. So this does present a few potentials for things like DOS and man-in-the-middle attacks. Because if the router is not IPv6 enabled, your router solicitation messages are still going to be sent. You could have a rogue device acting as a gateway, sending out invalid router advertisements. That would be a man-in-the-middle type attack. The router solicitation will go also to the router, but if it's not an IPv6 router, it will not respond with the router advertisement. So even if the router is not IPv6 enabled, our clients typically are. So this has the ability to do a DOS attack on clients, or at least a man-in-the-middle type attack. The mitigation techniques such as RA guard is an option, which we're going to talk about that in a later chapter. So again, we've talked about SLAAC with DHCP under the global unicast address, specifically with dynamic addresses. And again, all of the additional stateful functionality will be a later chapter. Lesson 8. Thank you. Again, all of this came from the IPv6 fundamentals, all written by Rick Graziani. Here's all of his additional material. And again, all material for this chapter goes to Rick Graziani. I want to thank you.